and talk about our pairs. Right? At this point in time, everybody should have at least one glue stick per table, hopefully more. You're going to have to share with your friends, okay? Because we don't have enough glue for everyone. So the first one we're going to talk about, 4 less than a number, all right? So we could go ahead and glue this match down. 4 less than a number. All right? Now, let's talk about what this model means. 4 less than a number. Do we know what number they are talking about? No. So what did they call that number?
Number 4.
N. Good. So 4 less than some number. We don't know what that number is, so we'll call it N. Now, to model that expression, it's fairly straightforward. This shows the whole of N and then 4 being taken from it. So for subtraction expressions, you're always going to have some whole value, whether or not it's a variable or a number, that's to be determined, but some whole value and then a piece being taken from it. So the correct expression was 4 less than a number. And if we wanted to make that look all mathy, okay, and actually put some numbers down, underneath where it says first match, I want you to write N minus 4. That is our first expression we are writing. So N minus 4. Now, what is, could you make this more, could you take this and make it more simplified? Or is that as simple as it goes? You could simplify that? No, because what do I need to know in order to get an answer to simplify it? Perfect. I need to know what that number is, what N is. What if I told you guys that N is 10? What would your answer be?
6.
6. Perfect. Okay? That's kind of what we're moving into. We're going to be moving into writing expressions and then solving or simplifying them. Okay? So 4 less than a number. That's our first example. Next example. 2 times a number subtracted from 3. So in this case, guys, the whole is represented by 3. Okay? The next specific thing it says is 2 times a number. Do we know what that number is? No. In this case, they called it x. So you have the whole of 3, and then you have 2 x's being taken from it. Those 2 x's are put together in one piece, all right? You could say it's x plus x, but we already had this discussion last week or the week before, I can't remember. Repeated addition is the same as multiplication. Good. So that is 2x. So to write this as an expression, you would say 3 minus 2x. Do we know what x is? No. Can we solve for x? Could I solve for x right now? 3 minus 2x. Could I figure out what x is?
No.
No, I couldn't. What do I need in order to solve for x? You're on the, I like where your head's at today, Courtney. Finish your thought. Just show me. What is, okay. All right. So what do I need?
You need an x right here and then it like equals in a number.
Perfect. So what he just said is I need an equal sign. So say for instance up here, my n minus 4. If I had an equal sign, so some number minus 4 gives me 10. What number minus 4 gives me 10?
12. 14.
14, perfect. That's an equation. So the difference between an expression and an equation is that equal sign. For right now, we're not doing equations though, so don't worry about that. Okay? I'm trying to erase it, but you know, the board's just special. So. Okay, so moving on. The third match, a number multiplied by 3. So in your third match, the whole is made up of a combination of 3 x's. Now you could argue that this is x plus x plus x. But again, let's bring it back to, that is equivalent, that simplifies down to 3x. All right, so my next expression is 3x. All right, so fourth match. The sum of 2 and 3 times a number. So in this expression, my whole is made up of a combination of 2 and 3 times some number m. This is an addition expression. The whole is made up of a combination of 2 parts. So to write this expression, I would say 2 plus 3m. 2 plus 3m. So the big difference I'm seeing between addition and subtraction. For subtraction, all right, you have the whole and you're taking a part from it. For addition, the whole is made up of a combination of several pieces. So we've modeled addition, subtraction, multiplication, because multiplication is just repeated addition. All right. Our last example is some more addition. We have a number added to 4. So again, the whole is made up of a combination of some number being added to 4. So my expression would be 4 plus b. Wouldn't it be b plus 4? Could you say b plus 4? Is that equivalent?
Yes.
Because of what property? Commutative property of addition. Good. Okay. Now that sixth and final match, or I guess sixth and final expression, we have a whole being made up of 6 and the letter K. Does anybody think that they have an expression written correctly that represents this model? Mark? A number added to 6. Is there another way you could phrase that? Yes, Shamil?
The sum of a number and 6.
The sum of a number and 6. Both work out, okay? So you could say the sum of a number and 6, or you could say, or a number added to 6. So either of those are correct. You guys, oh, I forgot this part right here. So this would be 6 plus K. Yes. Yep. So you guys need to take a second and make sure these are all glued down and written out. When you are done with that, we're going to flip over and keep working, okay? On to the back side, guys. So we have just successfully written algebraic expressions. If you notice, every expression had 2 things in common. Number 1, they all contained at least one variable. And remember, if you forgot what the variable is, the variable represents the unknown number. It's the letter. Okay? So they all had at least one letter. All right? And they all had at least one operation. Sorry about this board, y'all. So one variable and one operation. Remember, operation is addition, subtraction, multiplication, or division. Now, if you're really paying attention, you'll notice that we didn't model a division expression. We're about to do that. But before we do that, I want to touch base really quickly on multiplication. any letter can be used to represent a variable, but the most frequently used letter, guys, is typically X. Does anybody think they know why? Courtney, you're on a roll. Let's hear it.
X because it's the second last.
Courtney, I'm going to just pretend like the last 30 seconds didn't happen. Yes, Mark, why? Yeah, because of the coordinate plane. So that's what you were trying to say, right?
Yeah, but they don't use
So,
one. It's just
that's what, if y'all, so X is the most frequently used variable because of the coordinate plane. And what I was going to ask is, so what do you think the second most used one is? Y. Okay. So, to represent multiplication, yes.
Why does X become before Y? Why does X become because 7, 8, 9.
I feel like you're about to tell me like X, Y, Z or something. I got really. Okay. So, when we are writing multiplication, a lot of times you'll see y'all want to write, so if I said 3 times X, y'all would want to write it like this. 3 times X, but that's super confusing. Okay, so we are no longer using that multiplication symbol as a X. Okay, so a lot of people want to say, all right, well, 3 dot X or 3 parentheses X. That's great. Both of those simplify down to just 3 times X, written like that. So anytime you see a number attached to the variable like that, that means 3 X's or 3 times X. Really quickly, I do want to touch on, as you are getting more into writing algebraic expressions, you're going to have more freedom to use your own variables. Some commonly confused variables. First really confusing variable is the letter T. Notice how I wrote it. When you're writing expressions, you want to make sure that you write your letter T with the little curl or use a capital T because it can look like an addition sign. Okay, so be careful with the letter T. A lot of times when you're writing an expression for like the total of something, you'll say let T equal total, and then you get super confused as you're working because it looks like plus plus instead of T plus or T minus, or I guess minus would be confusing. Okay, so T is a common variable that people get confused with. Another one, when you're writing an expression for say length and width of a rectangle, L gets really confusing, so we want to make sure that we use the cursive L, all right, or a capital L. Just make sure you don't just write a line, because a line is going to look like a 1. And on that note, the variable O, which I very seldom have seen used, but if you are using an O, please make sure that you write a cursive O. Otherwise, it will look like a 0. You're writing this down. If I'm writing it down, you're writing it down. Where I'm writing it, on the paper. Okay? And then, finally, what letter could look an awful lot like a 2, depending on how you write your 2? A Z. So in math, we're going to write a Z with a line through it. Okay? So that way, if you had the expression 2Z, it wasn't confusing like this. You're like, huh? That looks like 22 with a big 2 and a little 2. So 2Z with the line. Okay? So just a little tidbit as you guys get started writing your own expressions, some commonly confused variables. Okay, if you look down, the rest of this is your homework. Now, it's fairly straightforward, just like the front. You have the algebraic expression, then you need to write the phrase and the model. Now, if you look, flip back to the front, we have subtraction, multiplication. Oh, look, it looks exactly like this, doesn't it? Subtraction, multiplication, addition. So if you were confused, flip over to the front side. Now, the only one we don't have an example of on the front would be number 4, this division. you would read this as a number divided by 3. A number divided by 3. So we don't know how to model division, but if you look down at the 4 remaining examples on the homework where they want you to work backwards from the model, let's go through and let's discuss the ones that we do know. So number 6, we have a whole and we have a part being taken from it. What operation is that? Subtraction. So number 6 is subtraction. Y'all are going to have to go back in and fill the pieces. Number 7, we have a whole being made up of 2 parts being put together. So what operation is that? Addition. Number 8, I have no idea what that is. So, what do we think that might be? Division. Okay. And then number 9, I'm going to go ahead and tell you. So we have a whole being made up of 2 different parts. It looks an awful lot like your 4th example. Okay, so if you want some help, maybe make a little note. Number 9 looks like your 4th match on the front. So you have a variable and okay. So we do not know how to do number 8. We decided that number 8 is division. So it looks like we could say, all right, well, this is a number divided by something, right? A number divided by. Now let's figure out what it was divided by. So in the diagram, or I guess the expression model for number 8, you have a whole, and then right beneath it, you have an equivalent size whole cut into how many pieces? 4. So this is a number divided by 4. Okay? So then to write the expression, you're going to say some number m divided by 4. Now notice, I wrote that as a fraction. All fractions are division, okay? You could go through and you could say m divided by 4. However, mathematically, you need to get comfortable with the concept that fractions are division. All right, so m divided by 4 is how I prefer that, m over 4. So then, going back up to number 4, let's draw the model now that we have number 8 as a reference. So we start with some whole. In number 4, they called that whole C. Okay, and then we have an equivalent sized model below, except this time, how many parts are they cutting C into? 3, good. So I'm going to cut C into 3 pieces. I'm going to circle this to show, hey, this is what I need to be drawing my focus in on. So some number C divided by 3. So all y'all have to do for homework then is go through and fill in the missing pieces. So number 2, 3, 5, and then we already talked about 6 through 9, so it should go very quickly tonight for you. Okay? So set this to the side. We're going to now go to the pages from our module that you tore out. So we're going to start on page 39.
We're going to continue working on what we just did by doing more of these models and diagrams, and we're going to talk a little bit more about why we're putting them together like we are. So our next one, and this goes by and large mathematically. As I read it in English, I'm going to write it in math exactly the same way in the same order, with a few exceptions that we'll get to. So our first one, we're going to do a bar diagram, which is what those models we've been showing you are, that shows 3 plus 5. So using our model, what would go in our first box? 3. What would go in our second box? 5. So we're getting away a little bit from doing all the individual boxes, guys, because we're going to be using a lot bigger numbers, and we're going to be using a lot more of variables. So we need to make sure that we can do this. Would this look different if I did 5 plus 3?
Yeah.
Why?
Because the 5 would be first.
Good, because my 5 would go first, and the 3 would go second. Are these two expressions equivalent?
Yes.
Why?
It doesn't matter the order that you put them in, they're still going to be the same.
What property says that?
Commutative property of addition.
Good. So yes, commutative property of addition. Now, that being said, is there a right and wrong way to write those models?
Yes.
Yes, because of the way they're written, it really should be the 5 plus 3. So on addition, though, I would probably take the first model if it was 5 plus 3 because it would be equivalent. But realize your model should actually mirror exactly how it is written. Now, how can we show a number increased by 2? So what would be a number? N, okay. Increased 2. So does that expression show a number increased by 2?
Yes.
Mary? No, that's when you're defining your variables. Do we know what n is? No. So if I'm building an equation, absolutely. But we're just doing expressions, so this doesn't actually stand for anything yet. We just know that there's some number there. Now, can we do this with a model? Could I do a model on this? What would it look like, Wyatt? N in my first box? And the second box is just attached to it. What's a 2? Pretty easy, right? Okay, ready to turn the page? Now, let's do another one. Let's go to expression. Show the sum of m and k. Sum means what?
Subtraction.
Addition. Difference would be subtraction or subtracted. So what am I showing for the addition? We're doing m and k. And I just did that wrong because it said write an expression. I did a model. So m plus k would be the expression. Now, what property can we use in all those examples to show that they're equivalent? Good. We'll write it again just because I want to make sure you guys start to really get that in your brains. Commutative property of addition. Yes, ma'am. I'm sorry? No, I want you to get those words down. Commutative property of addition. How can we show 10 minus 6? Let's draw a bar diagram first. So from the models we've already shown you, what's going to go in my top box? 10. Then what am I going to do? Then put a line down. Then a 6, showing that 6 is being taken from the 10. Does that make sense to everybody?
Yes.
So what all that model is showing me is I have this number, and I'm taking this piece out of it.
So you're taking 6 out?
Taking 6 out.
Okay.
So what expression would represent this model? Now I'm going to write this in math. How do I write this in math?
10 minus 6.
Really simple. 10 minus 6. Could we also use 6 minus 10?
No.
Why not?
Because it'll be subtracting. You can't have
So you're saying we'd get a different answer, right?
Yes.
Talia, why is that? But this is subtraction. Do we have a commutative property of subtraction?
No.
No, and this is exactly why. So really, could we also use 6 minus 10? No. I'm going to add this. There is no commutative property of subtraction. That's why we have to say, we can't just say commutative property, because not every operation has a commutative property. There is no commutative property of subtraction. That's also why we don't abbreviate. Okay? Our next one has two very, very important words, guys. Those two important words are less than. Less than is what we call a switching phrase. So please add this into your notes. This is a switching phrase. What that means is I'm going to reverse the order of the numbers. So 3 less than a number means those two are going to be swapped around. So we're going to start by drawing a diagram to model the subtraction. Here's our key. Are we taking away from the 3 or the unknown? Taking away from the unknown. So my top box is going to be what? N. Okay, so we'll use N for our variable. It's a subtraction model, so I'll draw a line. What goes in the bottom one? 3. So what expression would represent this? N minus 3. So sometimes that can help you. Guys, I want to just add one. Do me a favor and write over here switching phrases. I'm just going to give you a few of them. There are more, but the most common you're going to see are less than, more than,
He's writing, you're writing.
subtracted from, added to. So those are some of the 4 most common switching phrases you're going to see. Another key thing, what's missing? Would this be different if I said 3 is less than a number? Yes, because if I said 3 is less than a number, it would be 3 is less than a number. So that word is also makes a big difference. Okay? So on the pre-test you guys took, we had a problem very similar to this. I saw a lot of answers that looked like that. I think part of it was because we had just finished up inequalities. But a key word missing there is. So technically that is not correct, because it didn't have is in there, did it? Make sense, guys? Everybody good on this? Okay, let's go ahead and turn the page. Oh, we did.
We did.
We did the bottom question. N minus 3. Okay, here we're going to do another one. We're doing an expression, meaning we're writing it out mathematically. The number C being subtracted from the sum of A and B. So we're going to start this with that. Here's another one we're going to get, guys, is these joining words. These joining words, like from a quantity, stuff like that, means you should start thinking parentheses. Okay? So we're going to start with an expression for the sum of A and B. How would that look? Riley? A plus B. Everybody okay with that?
Yeah.
Now we're going to show C being subtracted from the sum. So we're going to go the A plus B and subtract the C. Do we need parentheses?
Yes.
Why?
Because you have to.
Why?
So you can get it.
Mary? The A plus B is first, right? So, what would I use to be able to solve this? I'll give you a hint. We just did 2 worksheets on it. Gemma, what do we call that?
After of operation.
Order of operations. So order of operations, how would I solve this?
Addition and then multiplication. Addition then.
This is subtraction on the same line, right?
If you have both, then you have to subtract.
Addition, left to right.
Left to right. So would A plus B minus C change if I had that in parentheses?
No.
Yes. Or no, because
No.
parentheses was first.
The parentheses are first. I'd still add the A plus B first, right?
Yeah.
So here's a little Mr. Moore, guys. A little more Mr. Moore tidbit. Because of the way it is written as subtracted from the sum, I personally would have gone ahead and put the parentheses on there.
Yes.
Does it make a difference in the long run? In this case, no. But I'd rather have the parentheses and not need them than not put the parentheses and have them be needed. Because of the way it's written, that is putting that sum together. Why is that important? So look at our next example and it'll help show why this is important. So now we're going to do an expression to show the number C minus the sum of A and B. Waffles? I'm sorry? Okay, talk to the people at your table. Talk to the people at the next table over. Now, how is this one going to look? Do what? C minus A plus B in parentheses.
Yep.
That?
If it didn't have operation.
Oh, A and B in parentheses.
No, because we can look at because if you have subtraction false, you have to find something that and subtract.
Okay. Why are the parentheses necessary in this example and not the others? Why?
Because you have to add and actually get a number to subtract.
Good, because I need to add first. So let's make it simple. It's really order of operations is the reason why. No, because you won't know what that is. I need to add first in this case. Okay? So let's replace our variables, and this is what we call substitution, guys. Basically, I tell you a value of a variable. So we're now going to put values to the variable. We'll say C is 8. We'll say that A is 4. We'll say that B is 2. So what we're going to do now is actually substitute those numbers, those values, in for the variables. So for our first one, for example, 8 minus the quantity of 4 plus 2. What is the first thing I do according to order of operations, Bubbles?
Do what's in the parentheses.
Good, so I'm going to do that first. So I'm going to rewrite that, 8 minus 6, which would equal 2. Now let's take away the parentheses and see what happens. 8 minus 4 plus 2. Now again, following the order of operations, what's the first thing I will do now?
Addition.
Subtraction, because addition subtraction goes left to right, correct?
Yes, you have both.
So if I have both, 8 minus 4 is 4, plus 2 is 6. Did I get the same answer?
No.
No. So were the parentheses necessary?
Yes.
Absolutely. Does everybody understand why?
Yes.
Anybody not understand why? Really important that you put those parentheses when you need them. Okay, number one, right? Expression to show the sum of 7 and 1.5, or 1 5/10. That should be super easy. Is there anybody that would struggle on that?
No.
I hope not. Let's turn the page and see how we're doing on this one. Okay, I'm going to cross out number 2, mostly because I don't like the fact that they're saying that the way you write it doesn't matter, because to me it does. So we're going to start 3 through 5. I'm going to give you guys 3 minutes. You can work together at your table. Write up the expressions for those. Okay, hopefully you guys were able to do this one really easy. Show the sum of A, B, and C. That was straightforward. A plus B plus C. 4 and 5 is where we get into a little more complex. This one, I had two things, right? An expression and a model showing 3 less than P. This right here should have set off warning bells. That's a switching phrase. So, because I have a switching phrase, that's the time that my order changes, meaning that my model should have had the P on the top, and then my line with 3 being taken from it. That is different than this one, where I just do the difference of 3 and P. Because of the way they wrote that, it is a different expression. So yeah, I have a hard time believing you're talking about what I'm talking about.
Making a song with it.
Yeah. Okay, let's go ahead and make sure you got that. Turn the page again. Okay, you've got 3 more on this page. I'll give you 3 more minutes. Okay, let's look at this one real quick. Number 6. An expression show 4 less than. Alarm bell should go off. Sum of G and 5. So that means I have to have the G and 5 first. 4 less than that. Next one, expression to show 4 decreased by the sum of G and 5. So now we're switching it. 4 decreased by the sum of G and 5. Must I have parentheses on the second one? Yes. Should they look different? Absolutely, in multiple ways. So yes, they should look different. One has a switching phrase. That requires
Oh my gosh, you write so much in like half a second.
that parentheses be used. As long as you did something to that effect, you're okay. Okay? So, one of them, number 7, had, 6 has a switching phrase, meaning that the 7, you had to use the parentheses, make sure you added before you subtracted. Okay, on your homework, should be relatively easy, guys. Don't forget, you have to do the back page of the Modeling Mayhem. Then this is your second one. On this one, 2 expressions and draw a model. Number 1 is the only one that requires a model. All the rest, you're just doing the expressions. Okay, questions? Yes, Riley. You can do them on here. There should be enough for them.